have Mr. Yampolsky, who's going to talk about renormalization, hyperbolicity, and rigidity for analytic homeomorphisms of the circle.
Yeah.
Oh. I don't have any control over that. Who's...
Don't you like it?
Who? Yeah. Okay, once we get the music over with.
Okay, so... Well, I just thought it was so nice, right?
You can keep the music on, but then you have to sing your talk.
Oh, believe me, Lasse, I don't want that to happen. All right. Okay, now I think everyone is sufficiently awake. So thanks very much. Thanks to the organizers. Thank you, Luna. Thank you, Carsten, for having a birthday here. It's wonderful to be here, and it's great to be given a talk. So the two main topics of my talk will be renormalization and rigidity of circle maps. And I'm going to define both concepts, try to give you some idea of how they're related, and then I'll try to paint sort of a big picture of where the subject is right now and state some theorems. I suspect that the picture that I would like to paint is too big, so it probably won't fit in my talk, but I'll at least show you some parts of it. Okay, so let's start with rigidity. Let's start with an example. Okay, so the famous example is a theorem of Danjois from the 1920s. I think 1927, but I'm not entirely sure. And it states the following, that if F and G are circle diffeomorphisms, which are slightly better than C1. They're C1 plus bounded variation. So their derivatives have bounded variation, and their rotation numbers are the same irrational. So rho of F is equal to rho of G. And is irrational, then F, so then there exists phi from the circle to itself, which is a homeomorphism, which conjugates the two. So this is an example of a rigidity theorem. So the general rigidity, well, when we talk about rigidity in dynamics and geometry in general, we typically mean that a weaker equivalence relation in some class of objects implies a stronger equivalence relation. That's exactly what it is. So the equivalence relation here, and this is what, you know, this is always the starting point for homeomorphisms of the circle, is that they have the same rotation number, the same irrational rotation number. So this is known as combinatorial equivalence. Because by the classical results of Poincaré, this implies that the combinatorics, the order of the orbits of these maps on the circle is the same. And now this, and the same as just the order of the orbits of an irrational rotation by this angle. And so if you have enough smoothness, then according to Danjois, this pushes the combinatorial equivalence to a topological equivalence. And by the way, since I'm also going to be talking about maps with critical points, let me also formulate a more modern counterpart of this, which is the theorem of Yokos. And this is from the 1990s, I believe, which extends the theorem of Danjois to maps with critical points. And in that case, so the class that you need, so f and g should be sufficiently smooth. Let me say C3, although you can do less. And they are homeomorphisms. So they can have critical points, but they have finitely many critical points. And all those critical points are non-flat. And then the same is true. Okay. Now, of course, as all of you know, or as most of you know, both of these theorems have been pushed quite far in the appropriate smoothness classes under the appropriate conditions on the rotation numbers and so on. And I'll formulate some examples. So, for instance, right, so there are much stronger versions of these rigidity statements which give a lot more smoothness to the map phi, right, to the conjugacy. In both of these instances, and I'm going to give some examples, but of course I'm not going to mention all of them. So Danjau's theorem, so the stronger version of Danjau's theorem are various flavors of KM theory in one variable, and so with some conditions on the rotation number, going back to the work of Arnold, with some conditions on the rotation numbers, with some extra conditions on the smoothness, you can get much smoother conjugacies here than just continuous. And of course, here we go into the subject of critical circle maps, which is near and dear to my heart, and you also get stronger conditions. Okay, so that's as far as rigidity goes. Now renormalization. I really like this. This kind of gives some rhythm to the talk. I should do it more often. Okay, so I'm going to give you some indication, actually, of why these sorts of statements are true. So, how one could approach proving them in some systematic way, and also introduce renormalization along the way. Okay? So to do this, we need to talk about first returns of points on the circle. And these statements are purely combinatorial. You just need to know that the rotation number is irrational. So, right, so let's talk combinatorics of first returns. So if our rotation number is irrational, it expands into an infinite continued fraction with positive terms. Well, I'm going to take a representative of this in 0, 1, and this will expand into an infinite continued fraction with positive terms. Which I'll usually abbreviate like this to save space. And then, of course, we have a sequence of convergence, which are the finite truncations of this continued fraction, which give best rational approximations for the rotation number. And they're usually denoted by Pn over Qn. So this would be common from a continued fraction with n terms. Now, these are best rational approximations, and this translates into closest returns of points on the circle under the dynamics of f. Because remember, combinatorics of f within a rational rotation number is the same as a rigid rotation, right? So if you just want to know about the order of points, you just look at the actual rigid rotation. So the best rational approximations would give you the nearest returns. Now, if you have a point x, then these denominators Qn would be closest return times in the orbit of x, and they would occur sort of on opposite sides of x. Well, I mean, there are no really opposite sides on the circle, but you know what I mean. So this would be Fqn of x, and this would be Fqn plus 1 of x. Now, they're closest returns in the sense that nothing with so no smaller iterate can be squeezed between x and one of these, right? But they are not the only closest returns. You also get intermediate returns, which are produced by the recurrence formula Qn plus 1 is equal to Qn minus 1 plus a n Qn, right? So you can, Qn plus 2 is equal to Qn plus an plus 1 Qn plus 1, just so I can use this picture. So if you take this point and now you start iterating to get the next denominator, which is Qn plus 2, you have to iterate it by this iterate, right, which just means rotating this way. So Fqn plus 1, and you have to do it an plus 1 times, and you get to Fqn plus 2 of x. And all of these intermediate ones are also closest returns. Okay, so now we're good. So what this gives you, I mean, if you now you look at this picture and it gives you a partition. So this is known as a dynamical partition of this interval. Okay, and you can actually translate this dynamical partition to the whole circle if you start taking the orbits of these under all intermediate iterates of f. And so in this way, you'll partition the circle. Now, the order of these points, this is a good systematic way. I mean, it's certainly not the only way, but it's a good systematic way of partitioning a circle by the dynamics of an orbit. And now you have two maps, f and g, for which these pictures are the same, right? So they're the same topologically, if you like, combinatorially. So with G, the order would be the same. You would have the same returns, etc. And so to prove something, so this would be point Y. So to prove something like Danjo's theorem or its various refinements, what you need to know is that not only the combinatorics of these pictures is the same, but the geometry is right. So for instance, to prove Danjo's theorem, you need to prove very little. You just need to know that these intervals shrink to 0, right? Then you can construct approximate conjugacies just by identifying corresponding points at all levels, and this would converge. To prove something like smoothness, you need to know something better, right? You need to know that not only these shrink to 0, but they have approximately the same relative sizes. Okay, now when you start talking about this, it's convenient to introduce renormalization as a geometric tool. So let me define it. So here is a classical definition. We'll have several of them. So here is a classical definition of renormalization, which is enough for these purposes. You just consider a pair of, so you consider a first return interval around x. Actually, let me, I'll start doing it anyway. I won't be able to help myself. Let me always do this around 0. 0 doesn't necessarily have any dynamical meaning, but it's just convenient to fix the ideas, to pick a specific point on the circle, right? So we'll take angle 0, and that's where we'll do it. By the way, I hope none of you mind that my circle lies on a straight line, right? So, circle, I mean, I'm using R mod Z as my circle, but of course, this is canonical isomorphic to S1 via the exponential map.
But also this is very small scale anyway, so you couldn't tell the difference. You might just
You should sit closer, then you'll be able to tell the difference. Okay, fine. So, right, so renormalization. So I'll just take 0. I'll take no particular reason for the moment, right? I'll take closest returns of 0 on the opposite side. So I'll take fqn plus 1 of 0, fqn of 0. And then I'll do the usual thing. Renormalization is a rescaled first return map. And the first return map to this pair of intervals is a pair of maps. I mean, this is really easy. To get this point, 0 is translated, you know, think of the rotation. That this is, F is a homeomorphism of the circle. Its combinatorics is exactly the same as a rigid rotation. So 0 rotates here this way by the fqn plus first iterate, and there by fqn iterate. So the first return map of this pair to the left of 0 is given by the iterate fqn, and it will rotate it over like so. And to the right of 0, the longer interval, it's rotated by fqn plus 1 to put 0 at this point. And these two endpoints are the same. This is qn plus 1. Or qn plus 1 plus qn, whichever way you prefer. OK. So now I need to rescale, and this is where usually most of the difficulty is here, but will be easy. We'll just rescale the larger of the two intervals to 0, 1. OK, I'll keep 0 at 0. I'll fix the orientation if I have to, and I'll send this point to 1 linearly. OK, so I rescale, I don't know, 0 to 0. This to 1, this wherever it falls. This is a linear rescale, and this will rescale the maps. This is renormalization. So this would be the nth renormalization of F. Notice that the nth renormalization of F, even though F is a circle map, is not a circle map. It's a pair of interval maps. It's two nonlinear maps of the intervals, right? So this is a nonlinear interval exchange map. Well, unless F is linear, in which case it's a linear interval exchange. But the problem is, right, so the problem is it's not easy to glue this back into a circle. And you know, every time I've given these talks, I've talked about that, and so I won't talk about this now. I'll just tell you, it's hard. Well, I'll talk about this now, just for a few minutes. So why is it hard? I mean, there's an obvious way of gluing. You could use the red, whatever, the pink, this map as a local chart, right? You glue this with that. And that gives you a topological circle. In fact, it gives you a smooth circle if your F is smooth. It will give you an analytic circle if F is an analytic. What it won't give you is an affine circle, because F is not affine. I mean, the only exception would be if F is an actual rotation. And that's a problem, right? That's a problem because you have an ambiguity that's not easy to get rid of. So that's why renormalization is defined, at least classically, in terms of these pairs of maps. So it acts on pairs of maps of the interval. One important condition, which is another, which causes, I mean, one problem leads to another here, right? So you make this compromise, and suddenly you find that this has cost you. So what this has cost you is that to be able to iterate such things, you need the dynamics to agree at the ends, right? I mean, where the two intervals meet. And you wanted to agree to some high order because you want to pretend that you're iterating restrictions of a smooth map or maybe an analytic map. So what you want is not just a pair of interval maps, but a commuting pair of interval maps. So they only have to commute in the neighborhood of the point 0, which is the only place where the two domains intersect. So this is known as commuting pairs. The commutation condition is bad because in finite dimension it's, well, I mean, it's whatever. We'll get there. It's bad. All right, good. Now, the connection with rigidity should now be somewhat clear, right? So one way of saying that the geometry of these partitions is similar is comparing renormalizations of the maps. Because renormalizations of the maps, after all, are rescaled central intervals in this partition. So if what you care about is smoothness, you care about the relative sizes of neighbors in this partition. And of course, if maps converge sufficiently fast, then the relative sizes will be sufficiently close. So here's a meta theorem. So speed, well, first of all, convergence. You need renormalizations to somehow converge together. So speed of convergence of, well, let me write it like this. Distance between Rn f Rn g to 0 corresponds to rigidity. Okay, good. So I think I've made the definitions I wanted, and now let me, I mean, these are all, yeah.
When you say rigidity statements, are you saying like for various rates of speed, you can extract various degrees of smoothness? Is that what you mean by?
Yes, that is also true to some extent, although, well, I mean, in the KM setting, this is literally true. Okay? So for instance, if you look at Hani and Sinai's works on smooth KM, right, then this is literally what they do. So the speed of convergence implies improvement in smoothness of the conjugacy, phi. Okay? But in general, this should not be taken, you know, as a somehow literally true statement. I just wanted to give you some definitions and some idea for why I'm going to look at the theorems that I want to look at. Okay, so now comes sort of the main punchline. So the main punchline is that it is actually extremely useful, as it turns out, in this subject to look at renormalization not just as a geometric procedure, right, on comparing the geometry of first returns of the maps, but as an actual operator in some suitable Banach space, a Banach manifold of maps. And that change to that point of view really changes things. So let me give you some examples. So I would like to see this as an operator. So operator in a Banach manifold. All right. So there will be a difficulty. As soon as you want to take this point of view, there is a difficulty because you have to define a space of objects in which renormalization acts as a Banach manifold. So this leads to problems. For instance, you cannot take finitely smooth objects because the definition of renormalization involves composition. Composition is not smooth if you consider this as a map from CK times ck to ck. It's just not smooth. It's smooth as a map from ck times ck to ck minus 1. Students in the audience are welcome to check it right now. So, okay, in the infinite smoothness, you run into a different problem. Well, infinite smoothness. C infinity is a lost cause, so you have to talk analytic, right? So in the analytic category, you run into a different problem. There, the commutation condition is a problem. Commutation condition is an infinite codimension condition in the analytic category. Glue in this is not an option because even if your glue in is analytic, it's not a find.
I missed what you said earlier. Can you repeat what the commuting condition was?
Oh, commutation condition is just that, so you have a pair, right? So let's forget that this came from a map because now I want to define a space of abstract objects on which renormalization will act. So I'll just call them something. I'll call, I don't know, this iterate I'll call eta, and this iterate I'll call xi. So you have a pair at zeta, which is eta xi, which is like a circle map because you could use eta to glue the ends, and then xi projects down to a well-defined thing. But to say that, you need the two to commute at this point.
But they're maps on data and C are maps.
Yes, they're maps. They're maps, right. Yeah, but now you're using this to glue the ends, and for the map to give you a well-defined map, once you glue the ends, you need the commutation condition. So this commutation condition is just eta composed with xi is xi composed with eta, but it's kind of idiotic because it's only at one point. But that's already enough, right? If two analytic maps commute at one point, that's an infinite codimension condition. So it does not a priori give you a nice Banach manifold, Banach submanifold of the manifold of pairs of bounded analytic maps. So you need a workaround. Okay, so the first example I'm going to give you of this is in the Danjois setting, in the setting of circle differs, right? So the KM setting, if you like. So analytic circle differs. So the funny thing is that even though this is the more classical setting, the result is very new. So this is something we did with Natasha Goncharuk. And this is renormalization of analytic differs. Right? So now F so now F that we're going to renormalize is an analytic diffeomorphism on the circle. Therefore, it has an analytic continuation to some annulus. To work in some sort of a Banach manifold, we'll just fix the modulus of this annulus. So there is some delta such that, I don't know, I'll call pi delta. This is the annulus imaginary part of z is less than delta. Mod the integers. So F would be defined in here, and it's analytic, right? It's an analytic circle map. We'll just look at bounded analytic maps in this annulus. Okay, to define renormalization, we use a version of what I called cylinder renormalization way back when. So cylinder renormalization, in this case, would be quite simple. So your F, you should think of this as something that's fairly close to rotation, right? It's a differ, it's a conformal differ, which is defined in some fair size annulus, so there'll be some bounded distortion. This is not too far removed from a rotation. So what you will see is that if you take say, the red iterate, right? So if you take the iterate Qn, so here is your 0. 0 plays no particular role here. It's not a dynamically marked point, nothing like that. So if you take this, you know, you take a vertical segment. This is, I mean, this point, which way is my FQN going? That way. Oh, excellent. So FQN translates it like this. This thing becomes something else. But it's still nearly vertical. This is nearly rotation here, so it's nearly translation in the complex. So what we can do is we can somehow close the ends. This is topologically a cylinder, and we can uniformize it. We can uniformize it conformally. Let's call it, say, capital psi sub f into a straight cylinder. Well, sorry, into a cylinder which is not necessarily straight, because what I actually really care about, so typically when you do these things, like you know, this is, versions of this procedure have of course appeared before. Yokos, for instance, used a version of this renormalization, you know, in his works. But what I really care about is that this is analytic. The dependence of this on f is analytic. So and then you get an analytic operator. Then in here, this is an analytic gluon, but this actually is a subset of C mod Z. This has a canonical affine structure. This is a true circle. So this, the only thing you need to care about is that pi delta is a subset of this, but of course you guaranteed this near rotations. Rotations, just for rotations, you could take delta equal to infinity. And so this gives you an analytic operator.
Did you mean f from pi delta to pi delta?
No. No, I don't. Why? F is just an analytic map.
Is this real analytic or complex analytic?
It's a real symmetric complex analytic map of one variable. It's a map of one complex variable which happens to have real symmetry and preserves the circle. Okay? Yes, you can arrange that. This is just properly done quasi-conformal surgery gluing.
You want the same delta?
You want the same delta. In reality, I'm skipping some details because delta will depend on the class of rotation numbers. So in fact, you don't quite get the same delta, but you get stratifications by different deltas. Right, so the map, the first return map here, which we call G, this is a renormalization of F. Okay, so now we have an operator. Now we have an operator, an analytic operator from a Banach manifold to itself. This is a
I know you want to skip it, but so are you saying that the delta might sort of increase where it's defined, but it won't increase all the way down if you
Correct.
That's pretty nice.
Yeah, the delta wants to increase, right? That's what it wants to do. You think of this as a rotation. What are you doing? You're taking something vertical, right? Now you want to glue this back into a cylinder and rescale the width to 1. This rescaling, which is nearly linear, pushes the height way up. Okay? So no trouble there. Yeah. Okay, what is the upshot? What is the bonus for?
I'm sorry, I'm still lost on
No, that's all right. But maybe, yeah, go ahead, quickly.
homomorphic function that has real values.
I mean, I've been lost most of my life with this, so that's all right.
Don't we want a self-map here?
No,
You don't.
no.
You're discarding a coordinate somehow. You've got
I don't know what you're talking about, Adam. I don't know. I'm looking at an open set in a Banach manifold. What self-maps? Why would this somehow map some specific strip into itself? I don't understand. It maps the circle to a circle. That you get from real symmetry. You don't get anything else.
I just don't know all the facts. I just don't understand.
You're not getting anything else. Okay, what is the upshot? Okay, the upshot is the following. First of all, okay, this is an analytic operator. 1, this operator has an invariant set. This invariant set happens to be rational rotations. Obviously, if I do this with a linear map, then I'm getting back a linear map. On the rotation numbers, the action of this, as most of you know, is just the Gauss map. Right? So renormalization, so the rotation number of renormalization of f is the fractional part of 1 over the rotation number of f. In other words, we just forget the first digit in the continued fraction. What's that? Well, I mean, you could get a higher iterate of a Gauss map. You could get kth iterate of a Gauss map. But with this construction, you always get an iterate of a Gauss map. There's no, yeah. So, sorry, where was I? I mean, notice that I'm taking, I think I understand your question. If you take some other interval, like some other first return interval, some other interval in the orbit, you'll get something else, right? But I'm taking the interval which corresponds to the qnth return. Is that what you meant? Yeah. Okay, yeah. So, yeah, but for this specific construction, that's what you get. Okay, bonus that you get from here. It's an analytic operator. Moreover, it has an invariant set. So that's just irrational rotation numbers. Irrational rotations, I'm sorry. So if you take rigid rotation, capital R for rigid rotation, R theta of z is z plus theta mod 1. So this is invariant. And you can ask, as we often do in dynamics, what are the hyperbolic properties of this set? So to answer this, you need to restrict to some nicer rotation numbers. So, okay, sorry to the part of the audience who are going to get a little bit lost here, but at some point I have to start assuming some prior knowledge. So let's restrict ourselves to Bruno rotation numbers, which is the sort of the nicest, the weakest Diophantine type condition that's still useful for circle diffeos. So, and then the theorem that we proved is that the set R theta is in Bruno is a hyperbolic set of R with one-dimensional expanding direction. You already have one expanding direction. That's theta itself. On thetas, this is a Gauss map, so the rotations themselves are expanded. You just need to prove that everything else is contracted. But that turns out to be, I mean, it's our work, so I don't want to somehow say that any part of it is easy. It's all hard, but this part is not particularly hard. So it's not particularly hard to show that there is a codimension 1 contracting direction here. I can tell you specifically the contracting direction consists of vector fields with 0 mean, and you could show that these are actually contracted directly, more or less. Okay, now you have a bonus. This is a hyperbolic set, so we are going to get, okay, so uniformly if, so, right, I'm cheating a little bit. So this is like the question Mitsu has asked. So we have to actually stratify the Bruno numbers, okay, and by a quantitative Bruno condition. And when we do, then we get uniformly hyperbolic sets for each one of those, and uniform choice of the neighborhood for each one of those, and so on. I don't really want to go into these details, but yeah. Okay, so now here's a picture. So this is the theta axis. These are the Bruno rotations. They're actually dense here. And for each one, you are going to get a manifold, a stable manifold. So this is our theta. And this is codimension 1 in your Banach space. And this is an analytic manifold in the Banach space. Now, in the whole Banach space of maps of pi delta, we don't care about real symmetry anymore. This is an analytic operator. I mean, the invariant set happens to be real symmetric, but that doesn't mean anything in general. Okay, so the next theorem that we proved, remember I told you convergence of renormalization should imply rigidity, right? So now rigidity. So rigidity is the following statement: if f and g belong to the same stable leaf, then, well, actually, I should write if and only if f and g belong to the same stable leaf. One direction is almost trivial. If and only if f is conformally conjugate to g. So these are actually conformal conjugacy classes. The arrow up is almost trivial. So this is a stronger version of something that has been previously proved. This was proved by Rissler, who was a student of Yoko's, by different methods entirely. Well, different methods entirely because he used renormalization as a geometric tool and not as an analytic operator. So here we get that a very strong version of rigidity. You have in a neighborhood, so the neighborhood of rotations in just the space of analytic maps without any assumptions on real symmetry is foliated by codimension 1 analytic submanifolds, which are conjugacy classes, conformal conjugacy classes. Okay, so that's your rigidity statement. The fact that renormalization converges here implies so your hyperbolic picture is like this, and being in here means being conformally conjugate. Yes?
You can't take closures because this issue was not.
Yeah, well, I mean, you can't take closures because there'll be rational rotation numbers there too, right?
Well, still, I don't understand why it is that.
What? No, I don't quite understand. So,
Well, I live in a very, small world. So you're thinking like,
well, lucky you.
yeah, right. But, why can't you take closures and find rational rotation? What goes wrong with rotation?
Well, I mean, if you, a lot goes wrong. So once your rotation number is rational, you could only do this procedure finitely many times, right? You mean what degenerates with the analytic construction? You no longer will have a first return. You will have a fixed point. So this.
Picture the Banach space. What is it that?
Well, I mean, we. Yeah. Okay, but now those all right. So I'm not going to talk about how to obviously, you have to prove it, right? You have to prove that this convergence, I mean, the convergence of renormalization has to imply a form of rigidity.
This theorem is for all of your Bruno zetas.
Yes, 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 correct. Obviously, renormalization convergence should imply some version of rigidity in this class. This is a very strong version of rigidity. This arrow is not immediate, but I'm not going to talk about this part of the proof just for lack of time, because I want to draw at least a bit more of the picture, okay? So those, like the picture goes far. So let's push it a little further. Right, those of you who heard me talk about this before typically would hear me talking about maps with critical points, in particular with the single critical point, critical circle maps. So for critical circle maps, usually you put, so let's talk in the analytic category, okay? Usually you put the critical point at 0, and then 0 suddenly has a meaning. And you still consider renormalizations and so on. For the moment, for the next 5 minutes, only one. So let's look again in the analytic class. And it turns out that in the analytic class, there is also a hyperbolic picture. So except the invariant set is no longer rigid rotations. It's something much more complicated, but you could still do cylinder renormalization for analytic critical circle maps, same way. So here I'll take single, say, cubic critical point. Cubic because that's the lowest criticality you could have, and still keeping this a circle homeomorphism in the analytic category. Okay, so then it turns out, and this is also a joint work with Natasha, and this is more recent, and we're just finishing writing the paper, is that you can actually put the two hyperbolic horseshoes in the same space. So you could extend this picture to that one all the way. Okay, so you will have a hyperbolic. So let's say, let's pick some nice irrational. Let's say the golden mean that everybody loves. So this would be a fixed point. And there's a fixed point here. Okay, which is also, so it has an unstable direction which corresponds to the rotation number. It also has an unstable direction which corresponds to loss of criticality, and this stable manifold is global. It continues all the way. Okay? And, well, and then everything else is stable. So there are two unstable, and then there's infinitely many dimensions, but unfortunately the board is only two-dimensional, so I just ran out of. Let me draw a really thick arrow that goes in here. That's infinitely dimensional. So we get this picture, say, for all bounded type rotation numbers. So this gives, so for instance, there were conjectures of Delayave and co-authors based on computer experiments on the smoothness of invariant curves, say Arnold tons, at the end, right, at the ends. And we prove these conditions. We give an estimate on the smoothness, which comes from the comparison of the two unstable eigenvalues for the horseshoe here. Okay, so now, okay, let me now do pure hand waving. So now I want to, no, come on, there's no time. Let me do hand waving, and then you just Remember your question for the next 5 minutes, and then you'll ask me. Nah, I'm kidding. Go ahead. Ah, please. Ah, no.
What are the Banach spaces that you're working with, and if they go all the way to there?
Yeah, the Banach space is just a space of cylinder maps. Just take a cylinder, analytic maps, blah. Yeah, it goes all the way. You can pick your delta in such a way that it works for everything.
Is there any possibility that the picture can be continued even farther to the right? If there's any?
Okay, can I? So, I'm going to continue this picture a bit more. So, here's one way to continue this picture. Look, what are we seeing? Let's say we fix the rotation number. Let's say we fix the golden mean. Let's pretend that in the space of maps it gives us a submanifold. It should be a submanifold of codimension 1. Rotation number is really a very crappy parameter, but it actually happens to be true. So in this submanifold, you have a sink for renormalization, which is the rotation, right? And it has an open basin, this sink. On the boundary of this basin lives this hyperbolic point. But there are many other hyperbolic horseshoes on the boundary, at least there should be, that correspond to higher degeneracies, higher criticalities. So for instance, you could put 2 cubic critical points, right? You could put 10 critical points. You could change the criticalities of the critical points. All of this should lead to degeneracies. How far can we push this picture? So with 2 cubic critical points, so this is what we call bicubic maps. We have 2 papers, one with Daniel Smanni and Gabriela Esteves, in which we construct the horseshoe itself, and then with Gabriela where we put the hyperbolic structure on the horseshoe. So this works. Higher criticality. Higher criticality, again, on a recent result with Igor Garbovitsky, we in fact construct the horseshoe for analytic maps of arbitrary criticality. So it doesn't matter how many critical points you have. Of course, you will have more unstable directions. There will be more combinatorial invariance. Critical points have to be in the same place, meaning that the order of the orbits on the circle should be the same, their criticality should be the same, and so on. And then they will sit in the same stable manifold. We don't construct a hyperbolic structure on this yet. We're working on that, right? Hyperbolic structure in the Banach space. This is purely a convergence statement. Okay, what kind of rigidity do you get out of this for maps with critical points? So for maps with critical points, convergence of renormalization, exponential convergence of renormalization here in this world. Is equivalent to C1 plus alpha conjugacy. So phi is C1 plus alpha at critical points. So that's what we get. This is known as C1 plus alpha rigidity. This is the best rigidity statement you could have if you have critical points for various reasons. Plus alpha just means there's an alpha Holder condition. C1 plus alpha at critical points. Everywhere else depends. If you're bounded type, then C1 plus alpha everywhere. If not, you can only push everywhere. You could push to C1. It's the best you can have. Yeah. Yeah. Right. So phi is always the same. It's the conjugation between the maps. So if they lie in the same stable set, right, in the same universality class, in the same stable set of renormalization, you should get a rigidity statement out of it. This is what you get with critical points. This is what we get here. So let me just make one more statement here. The picture is sort of infinitely large. I'll give you some maybe indication of how large by 2 minutes of hand waving. But before that, let me also say that we push this, in fact, to C1 plus alpha rigidity for smooth maps. So say C3 maps. This requires a different definition of renormalization, one which I don't have time to talk about, which is another workaround of the business with commute pairs, which is actually quite classical, and this is known as almost commute pairs. The problem is the magic with analytic uniformization only works for one-dimensional analytic maps. So armed with that definition of renormalization that I'm not going to talk about, one can extend this to other spaces. So for instance, this picture can be extended, this whole picture, to two-dimensional sufficiently dissipative perturbations, like, you know, a no-type theory of Lubitsch-Martins de Carvalho. And this also has been done. So here we did this with Denis Gaidashev, and in this case, the stable manifold extends to sufficiently dissipative two-dimensional perturbation. So there are two-dimensional maps. So this arrow should get even thicker, right? Because I just enlarged my space to two-dimensional maps. And you again get a rigidity statement. In this case, the rigidity is not going to be smooth anymore. These are critical maps. The conjugacy is not going to be smooth, although it still exists, right? But it's topological. In this case, I have also extended it. And here you get Hermann rings. Here you actually do get conformal pictures. So you have, so this arrow is also thicker. So this also extends to two-dimensional. Well, any dimensional maps, as long as everything else you add is sufficiently highly dissipative. So, OK, so for those who know, I should shut up here because this is, I spent too much of your time. The music has stopped. That's my cue. So one more thing I want to say. Well, two more things I want to say. So the first one is I completely haven't mentioned that one can extend the cylinder renormalization business to horseshoes which are not real symmetric, to Siegel disks, right? So, and this is like the work of Misha and Dima. I think Dima will probably talk about this maybe. So I haven't mentioned this. This could be, if one is really ambitious, this could be extended further to things like conservative maps in 2 dimensions, so stuff that's near and dear to Denis's heart. Yeah, so the meta theorem, the principle is always the same. If you get a nice horseshoe structure for renormalization, this will give you a foliation by stable manifolds, which these manifolds are conjugacy classes. I mean, the smoothness of the conjugacy, that depends on which class you're working in. But you are getting a rigidity theorem in this way. OK, so that's the first thing I wanted to say. The second thing I want to say is happy birthday, Carsten. It's great of you to celebrate it with all of us in the tropics. So thank you very much.